mechanism that shows an enzyme that's free. It's going to find a substrate in the solution, and together they're going to form this enzyme substrate complex. The enzyme substrate complex then has a choice. The substrate can, leave, coming back to a free enzyme, or this is a reversible process, or the substrate can be converted into the product, giving back the free enzyme. I don't know, that's why I didn't do it. I pull it out the wall when I'm super pissed at it. It doesn't work. It used to work, but that doesn't work. What? It doesn't work? I swear it doesn't work. Okay, please come back anytime the bells are rung. So each of these is considered a mechanistic step, and as mechanistic steps, I'm actually able to write down the rate law, because I'm going to do that in topic 16. Remember? So how would I talk about the rate of this reaction? I think there are two formulas, two ideas that we have about rate. I will take either of them right now. I want to know, what is the rate of product formation? The rate of this reaction. How fast do I make P? Doesn't seem like that crazy of a question.
Is it like the reactants, the power, or not the other one?
Okay, so I think you're trying to convince me that I could write that the rate is equal to K2 times the concentration of the enzyme substrate complex. The rate at which I make product, if this is a mechanistic step, is equal to the concentrations of the reactants raised to their stoichiometric coefficients times some rate constant, and I already named it K2. I think you could also say it's the change in concentration of the product with respect to time. That's why I said there are two ways, and I would take both answers because I don't know how to effectively answer that. So I would call that the rate law. I unfortunately don't know how much enzyme substrate complex there is, because the enzyme substrate complex is both being created by K1, but also it's being not quite destroyed, but it goes away, either with the substrate falling out or the product being formed. So what is the rate at which we make enzyme substrate complex? And what is the rate at which we use enzyme substrate complex? So if I wanted to know the change in its concentration as a function of time, you guys have said that I'm going to be making it per this K1 reaction, but I claim that the enzyme substrate is also able to be unmade, and so I feel like I need to account for that if I'm looking at how that concentration is changing over time. So I could take minus K minus 1 times the concentration of the enzyme substrate. So that would be the rate of this reverse process. But also, I'm going to have minus K2 times the concentration of enzyme substrate. Is that reasonable? I know what we've done wrong. I don't like this. Fix that. we're minusing because that's the enzyme substrate complex being used up. So again, the enzyme substrate complex is formed if I look at this reaction, and it's used up if I look at that reaction or this reaction. So I have a plus sign for making it and two minus signs for using it up. There we go. Michaelis and Minton are famous because Minton's a lady and that's impressive. Maud Minton. For making an approximation that's known as the steady state approximation. So just like Henderson and Hasselbalch, what they did was talk about an approximation that they could make in solving a Ka expression. These two are famous because they decided to make what we call the steady state approximation. What? Yeah, the steady state, huh? Did you guys know that you're actually in a class that's called applications? I think there's one more thing that I know. So this is the approximation that's a little bit famous, again, the steady state approximation. But I also know that into this vessel, I had to add some amount of enzyme. So like you take a scoop of catalase and you know how much it is, or you take some peroxidase, you know how much it is. And so I could tell you that the amount of the free enzyme plus the amount of the bound enzyme is equal to the total amount of enzyme I added. This is the same thing we did for the glycine. We said the amount of protonated and deprotonated glycine had to sum to 0.5 last class. That's how much glycine we had put in. We didn't know how many pens had caps or not caps. This is that same idea. We don't know how the enzyme is in the solution, but we know all of the enzyme has to be either free or bound. So again, that's what's interesting here. This is going to help us. But I wanted to talk, I guess, about what we remember from topic 6 kinetics and what hopefully we're going to find in topic B7. In topic 6, you guys learned about how the rate of a reaction changed with the temperature. And you guys learned about how the rate of a reaction changed with the concentration of reactants. And so I wondered if we could draw those pictures to help each other remember what we used to know how to do. I think these pens will work. So you're actually describing the biochemistry version of this. So I'll give that to you. That's the picture you described, right? So why is there an optimum here?
That's where the enzyme works the best, I guess, or has the highest rate of reaction.
That's right. So this is where the enzyme has the highest rate of reaction. As we increase the temperature, we expect the rate of a reaction to increase. But what happens to an enzyme is that it denatures. If you give it too much kinetic energy, it overcomes the potential energy of those tertiary structure interactions and starts to denature. What would it look like if I just had, manganese dioxide? Presumably it would just keep going up. We learned yesterday it's a concave down kind of graph. It makes sense if you think about it for a while, but Lord knows I didn't know it until we looked it up.
Concave down.
The second derivative is negative. Do you like that better?
No.
Okay. What? Is it a logistic function? I mean, no. If you want to, I think I should draw it like that if I was a better person, but it has to start smooth. I don't know. This function is going to be what I graphed on my calculator to to decide how to draw it because I was nervous, is that the rate is equal to K times the concentration of something, but I'm not changing the concentration in this picture, so let me ignore that for a minute and say that the rate, what's changing here is the temperature, so it's going to affect the rate constant. So I can write that the rate is proportional to the rate constant in this experiment, and the rate constant is of course given to me by the Arrhenius expression. Now, I don't know the activation energy for this particular thing, but I do know that the form should go as e to the minus 1 over t. And so I just tried to graph e to the minus 1 over t. It'll look kind of like that. It made sense that it doesn't plateau. It does, maybe it does eventually. I don't think it has an asymptote, but I know that it gets less and less steep. If you have something that's very cold and you give it some temperature, it's going to go a lot faster. If you have something that's hot and you give it some temperature, it's not going to affect the rate as much. And so that's why you see the slope of this thing getting smaller. Or that's what seemed reasonable in my head. How about a graph from chapter 6 about rate versus concentration? Okay, so you're again over here. You're going to be my master at this side. So you don't rush you. And she is imagining a curve that looks like this, where there's definitely a plateau. That's what we're trying to model using that approximation that's on the board. We're trying to understand the shape. But I wanted to remember what some of the shapes were, yesterday before we learned this, or before you walked into your biology class. What were some legal relationships between rate and concentration? There were only 3. I'll take it. No, it is not. It's a parabola. So it's going to be a 0th order, so the rate is just equal to some constant we call K. A 1st order, the rate is equal to K times the concentration of the reactant raised to the 1st power. That's the equation for a line that passes through the origin with a slope of K. Or 2nd order, in which case you have a parabola that passes through the origin as well. And so what I was hoping we could do is try to understand why enzymes have this different behavior. For relatively low concentrations of the substrate, what order do they seem to follow? And for relatively high concentrations of the substrate, we tend to say that the enzyme is saturated, and so it doesn't matter how much more substrate you put in there because the enzyme is full, and so it becomes so at low concentrations of substrate, we see a 1st order reaction. But at high concentrations of substrate, our argument is typically that the enzyme is always bound. So it doesn't matter how much more substrate we put in. And so I said, what is the order now with regard to the substrate concentration?
0.
And everyone didn't scream 0 last time, so I was sad and just trying to give you a shot. Okay. I don't know how much I want to math this. What is your feeling? You feel like doing math? So, I think the derivation is kind of fun because you've met me and you know that. But I know that you don't need to know it. So, I thought it was worth trying to remember how to write these rate laws from a mechanism. So that's why I didn't give up on that. I think it's worth saying that we have an approximation, like we can write down what they assumed. Again, a steady state approximation, the amount of bound substrate or bound enzyme is constant, is the approximation that they used. But now I think I'm just going to write down the answer. I really wish this answer was better. Go. And the answer is that the rate equal to some rate constant times the total amount of enzyme that I put in there times the concentration of the substrate divided by some new constant. It's a capital K with a subscript capital M plus the substrate.
Substrate.
Is that the rate formula that we have?
So that is what Michaelis and Menton figured out. The Km is called their constant. And again, depending on how hard we want to work, we can make some parallels between this picture and that formula. So on this axis, I have rate, of course. The Michaelis constant is going to be the concentration of substrate at which we have half of the maximum rate. So this plateaus at something we call Vmax, the maximum velocity of this enzyme. If we look at 1/2 that value, and we read off of our graph what the concentration of substrate is, it is equal to the Michaelis constant. So in some ways, the Michaelis constant is telling me about the efficiency of this enzyme. How much substrate concentration does it take to make this rate, half of what it could be? So we can imagine sort of two cases. So I have two different enzymes. I am looking at the rate of the reaction as a function of substrate concentration. Which one would you rather have? Which one is a better, more efficient, more magical enzyme for you? Yes, this one. Like it gets up to full speed much faster. So Km again is a measure of efficiency. But what would happen if in my just delightful set of equations that I know you enjoyed, even if you were too shy to tell me, I added something else? Now you have a system that has, 5 different equations going on at the same time. The enzyme can bind the substrate, make the enzyme substrate complex, which can then in turn produce the product. But the enzyme can also find a inhibitor, and when the inhibitor is bound in the enzyme is useless. Can you tell which kind of inhibitor this is? This is competitive. What we find is that when we have competitive interference, inhibition, sounds like the right word, doesn't it? Competitive inhibition, we get a curve that looks like this red thing. For competitive inhibition, what we observe is that it's like the enzyme is just a little bit less effective. I didn't know if you knew. I knew, but I really don't know how it's obvious. I think it's obvious because when the inhibitor is on the enzyme, I don't have any kind of pathway for the substrate to get there. And so it is out competing it. My understanding of the allosteric site, and again, different books seem to have different understandings, is that it doesn't so much prevent the substrate from binding. If you have something in the allosteric site, what it does is it prevents the substrate from making product. And so you can have a enzyme inhibitor substrate complex, we call it EIS, as you can imagine, and that simply can't go to product. And so you have this one's ability to get the inhibitor as well. So that is my understanding, and we assume that the K for the inhibitor is the same in both cases, and that's what we call non-competitive inhibition. So to write that down on the board, if we also have the ability to do this, trying to draw electrons, it's not going well. You guys might refer to that as non-competitive, or the kind where we have the allosteric site. And that changes my picture differently, actually. It ends like that the enzyme is just as good at doing its enzyme-y magic. However, there's something that's in the way. And the way that looks on my graph is like that. It actually has the same Michaelis constant, but it has a lower overall velocity. I think I drew it okay. If I arrow it in green, maybe someone in this world will be able to look at it again and know what I'm talking about. So again, to put in bold strokes what I believe you need to know where to draw a line showing me the Michaelis constant. Again, it's going to be the substrate concentration at which you are at half of maximum velocity of your enzyme. And then you need to be able to tell me the effect of adding an inhibitor. If we add a competitive inhibitor, we make the enzyme less efficient. That is to say, we make the Michaelis constant greater. If we add a non-competitive inhibitor, what we do is keep the enzyme equally efficient, but lower the overall maximum rate. There's a series of graphs that you can make. They're known as Lineweaver-Burke plots. In my past, I've done an experiment and asked you guys to do the Lineweaver-Burke plots. If we have time, we'll do peroxidase and perhaps make a graph and see the glory of it. It's fun. It's a fun lab. If we have a day for a lab, we'll do a lab just for joy. There's obviously no right out. Yes?
Is the y-axis of maximum velocity or
Oh,
acceleration?
it's just velocity.
And then so.
This is Vmax.
And with the non-competitive inhibitor, it has the same Km, but it doesn't reach the maximum
Perfect.
rate. that
Yes.
it would be.
Isn't Km half? Is Km half of the velocity?
Km is the substrate concentration at which we reach half of the maximum velocity. So in my green line, this is the maximum. So I reach half of the maximum here, and that's at that same Km as my original red line.
But it's like the value of the half maximum is not K.
That is correct. Km is a substrate. Km is reported in concentration units. I don't know if it honestly has units, but if it did,
Because I thought they were like the same thing.
well, we're the same way.
Like half volume and Km.
Velocity.
Or sorry, velocity. I thought they were the same thing, but since Km is something to concentration.
Does that feel better? Okay. Okay. I promise that's all you need to know. I also know that I find this interesting and fun to do for real, but I'm not having that day right now. And I think some of you are gonna start throwing punches if I start teaching you the things you don't need to know for my joy. I'm ready for you.
So to recap, the Michaelis constant is like a measure of like how efficient the thing is, and it's found at the substrate concentration at half the maximum velocity.
wants to be as low as possible.
Yeah.
Okay. So to do this, that is to get this graph, you would have to have a way of measuring the rate of the reaction. Did any of you do catalase peroxidase? Oh, you did it with like liver, right?
Yeah, liver.
So what did you measure to determine the rate?
I think gas, how much gas is produced?
That's right, I think you measured, I would have guessed oxygen, but I ain't gonna fight with you. You measure how much gas is produced, so you have a way of measuring the rate using one of the different Vernier probes. Because we are chemists and because we've been doing this since the 1950s, we didn't all have Vernier probes at that point. It's pretty common to try to make this something you could look for in a colorimeter or a spectrophotometer. So a lot of protein assays are done using spectrophotometers or light absorption. So to get the rate, you might be looking at the change in concentration of something, but that something is hopefully going to be colored. I can't do it, I'll be back. So in the experiment that I think some of you have done, whether it be with yeast or liver, I did it when I taught regular bio, so like, there's a chance you did this, Margaret, I just don't know. You do something along the lines of taking hydrogen peroxide and trying to turn it into water and oxygen. And so this would take peroxidase or catalase or whatever. Magic. Where do you get peroxidase? Potatoes, yeah. Just grind up a root vegetable, that's where you find it. So it's like, it's not exotic, it's really easy. Apparently you make a lot of hydrogen peroxide in your cells. I don't know why. What? Yes, but like, it's so unstable, it's so crazy. It seems like things would be much better if we didn't make that. I didn't think about spelling Gaiacol today. I'm putting a question mark because I made it up. The oxygen that is made is a process that we're trying to understand the rate of. In turn, will oxidize another compound and we'll see a color. And so I'd like to use the formation of this color as a way of seeing the rate of formation of oxygen, which in turn is showing me a rate of the breakdown of hydrogen peroxide. Does that make some sense? Enough sense? So I'm looking at the yellowness or the change in yellowness of this. So how am I going to do that? So I'm going to use a spectrophotometer. What a spectrophotometer is a light bulb. So we would draw like a white light. So we're going to pass the white light through a prism, and the different wavelengths, or frequencies, or energies, whatever you want to say, will be spread out. And so we should be able to see red, orange, yellow, green, blue, and violet. I can then have something that moves this way, which is just a slit. And that will choose a specific color of light. Because it's one, we call it mono. Because it's light, we call it chroma. So I have something that's known as a monochromator that will select one wavelength of light. What wavelength of light would I want if I'm making something that's yellow? That's right, I believe that it's going to absorb its complementary color. So if I were just to take an absorption spectrum of the Guycol in its yellow form, we expect that it's going to be some sort of beautiful Gaussian shape, normal distribution, however you guys call that, centered on purple, call it 450 nanometers. And so I'm going to use 450 nanometers to assess the purpleness of it. So now I'm a photon, I'm a 450 nanometer photon, if photons can in fact have wavelength. How many Guycol molecules can I interact with? One. I was gonna say, physics man, this is your moment to shine. There's gotta be a 1-to-1 ratio, because like when the light comes in, it's gonna move some electron around. The electron now owns that energy, it's gonna release as heat or whatever, but it's not gonna like still be that 450 nanometer photon. Ridiculous. So the amount of light that we absorb is directly proportional to the amount of particles we run into. So I'm gonna dumb this down and say 450 nanometer light's coming through. I just took the 450 light because it was too hard to draw. And I have these absorbers. And I'm going to have a detector here. I'm going to draw as an eyeball. I never know where to put the nose. It's not worth my time. Look at you. I'm going to see how much light comes through. So if there were no absorbers in there, presumably I would have all of the light that passed through. So we could talk about how much light is coming out here. And we could talk about how much light is being seen here. And I claim if those two values were equal to each other, it would mean nothing absorbed. What would happen if I had some absorbers? What would be true about this value? It would be smaller. That's right. And so we tend to take the transmittance to be equal to the ratio of how much light came out over how much light went in. And we take the absorbance to be minus the log of that ratio. So if the outgoing light is the same as the incoming light, and this ratio is 1, so 100% or transmission of 1, what's the log of 1? Everyone said 0. So no absorbance. Now what happens if the amount of light that comes out is 1 out of every 10 photons? The absorbance is 1. And if it's 1 out of every 100 photons, the absorbance is 2. 1 out of every 1,000 photons, the absorbance is 3. And so when you're looking at that absorbance scale, you'll usually find people who are trying to look for a number around 1 to 2. In like our little device, there's so much stray light in the room that if you're looking for 1 photon in like 10,000 to make it to your detector, chances are the stray light in the room is making it to your detector and you're not seeing it. So things get noisier and noisier as the absorbance gets higher and higher. But let's imagine that I put in some more absorbers. My absorbers are still absorbing the same color, but I'm trying to convince you that there are more of them. What is going to happen to the amount of incident light that comes out? Sorry. Go down. So the absorbance is going to go up. So it seems to me that the absorbance should be proportional to the amount of absorbers, and so we write that as the absorbance is proportional to the concentration of absorbers. This little thing is meant to represent a cuvette. A cuvette is a small, it's got a cross-section that's a square, plastic, like quasi-test tube looking thing. I know you've all seen them at this point. But if I were cooler, they make some that are differently shaped. What would happen if I put in like a long one, same solution, to the amount of light that went through? Less light would go through. Loudest is best. I like it. I feel like there's a lot of general agreement, but thank you. The amount of light that passed through would decrease because there are more molecules in my way. And so if the amount of light that passes through decreases, then the transmission decreases, and minus the log of it would increase. And so the absorbance is proportional to what we call the path length. In all of your experiments, that value was exactly 1 because we use cuvettes that are standardized so that we don't have to worry about that. So that's just a stretch. And there's one more variable here. It's a property of the material that is absorbing. Some things are just amazingly good at absorbing light. Examples of that, perhaps due to evolution, are chlorophyll, carotene. Like they're really good at it. But other stuff, they're not really good at it. If you use food coloring when you imagine Raimi making cakes, like blue food coloring, the one I used to use, it had a note on it, stains hair, stains nails, stains teeth. Like, don't mess with this one. You put in like the tiniest bit of blue and you get something that looks like radioactive. On the other hand, like the nice pink one, you're like scooping it in, trying to make pink because it's less good at absorbing light. We don't have a way to control this number. Its fancy word is molar absorptivity. C is the concentration of the absorber or chromatophore. So that equation is known as Beer's law, or the Beer-Lambert law. And so it shows me that the absorbance is directly proportional to the concentration. So typically when we're doing a bioassay like this, what we do is we make a calibration curve. In a calibration curve, what I'm going to do is I'm going to make standards of known concentration. So I'm going to put some of this stuff in, I'm going to oxidize the crap out of it so it's all yellow. I'm going to have a yellow solution. I'm going to say the concentration of this is 0.1 molar. I'm going to shove it in my spectrophotometer and it's going to have an absorbance. And then I'm going to take 10 milliliters of that, 10 milliliters of water, and shake them up and put them in my spectrophotometer. And the concentration of that is 0.05 molar. And if the world is a good place, it'd be right about there. And I will keep making this, and I will fit a best fit line through it. Now, frequently it won't stay linear at really high concentrations. Things get complicated. But usually over the range we're looking, we have a nice, straight, pretty calibration curve, and we do the linear regression and we find the formula for the line of best fit. So again, this is absorbance, this is concentration of my yellow stuff. And then what I'm going to do is I am going to run my experiment. I'm going to take one of the products of my experiment, and I'm gonna put it into my spectrophotometer. I don't know its concentration, but I do have the ability to read its absorbance. So I take my sample, I read it in here, it shows up at that point. I use my best fit line, and I can deduce that its concentration is 0.07. In this unit, you're supposed to understand the use of a calibration curve. Seems handy. And you're supposed to have some concept of Beer's law. Absorbance is proportional to concentration. Yes? So I got the 0.07 thing because I used my experimental yellow, and I plugged in its absorbance, so I knew its Y, and because I had this line of best fit, I knew the slope and the intercept, so I could solve for. So I'm just trying to.
Did you get that value from that, from doing the negative one or what?
I got that value from like physically doing this experiment and taking the product and then shoving it in my spectrophotometer to see what it said. Yes, so it is an unknown sample. B is the path length. So what I tried to argue is if I somehow made my cuvette bigger, but I put the same solution in it, it would have to travel through more of these molecules that absorb light, so less light would go through. I can do it the other way if that'll help. So your light coming through, and we're right now gonna hit like 1, 2, 3, 4, 5, 6 things. But if this cuvette were half the size, now we're gonna only hit 3 things. And so we would expect the absorbance to be lower, even though it's the same solution that's in there. So we need to know how long the light travels through the solution. Yeah?
Can you explain that T is equal to I over I?
So you last saw T when you were talking about infrared spectroscopy. I think that's probably why I talked about it. I don't know, it felt good, and then y'all made the faces like, why is she doing this to me? Do you remember that curve? So here we have something at about 3,200 centimeters to the minus 1, and here we have something at about 1,700 centimeters to the minus 1, and here we have a lot of jazz. And so this was wave number. This was transmittance, right? So all of the light goes through and I absorb by coming down, less light goes through. But when we talk about visible light absorption, we usually have a graph that looks the opposite way. So I was just trying to defend how less light is transmitted, but the absorbance is higher. Yes, like it's just a definition of how, like, it's just a straight definition.
What is I specifically?
What is I? So I0 is the amount of light that's coming out of my light source, and I is the amount of light that my detector measures.
Is it like in focus?
Sure. Or in intensity.
And is that what like a given number?
I do not believe that you will have those numbers. I believe worst case scenario, you'll have A, and you'll have to put a few points on a graph and draw that curve. But again, because we talked about the transmittance in IR, and it makes sense that I'm measuring the amount of light, I'm not directly measuring the absorbance. I was just trying to show that relationship, but apparently I shouldn't have.
Which you have to account for light absorption.
So that is why there would be a B term here. So we would expect that so like Beer's law says that the absorbance is directly proportional to the concentration. But when I got my line of best fit, I did have some background absorption that this line of best fit will resolve. So if you have something that accidentally does absorb where you're looking, you'll be able to cancel it out. And this is really a problem, as I was just describing, where there's a reasonable chance you're gonna have to graph some data and get your ruler and draw a line. Like this is rock star level biochemistry for the non-biochemist, right? Like Amarachi is ready to answer really difficult questions about the recombinant DNA stuff that's in this unit, right? And And Margaret is hoping that she gets to graph a line and take its slope because it's a skill she definitely has.
We're learning about recombinant DNA and
We do, isn't that magical?
Wait, seriously? Chemistry?
Seriously.
Oh.
Next unit, B8. Is that not what you were hoping for? I feel like you guys should be jumping up and down. You're taking a quiz on it like today.
Oh, bio.
Bio, isn't it non-recombinant DNA?
Wait, isn't it recombinant?
Yeah, like, you know how they get recombinant plasmids and stuff like that.
Oh, that's kind of different. Because it's like
How are you
artificially.
recombinant?
Or, yeah, like.
That's the same here. We're going to talk about genetically modified organisms.
Oh.
We're not going to talk about BT corn, but we are like
What about the potato,
my beautiful Amphora potatoes. Like, don't put that there because we're too dumb. So it says 2 benefits of genetically modified foods are that it can enhance flavor, texture, and whatever.
I thought we were talking about crossing over.
Like cotton candy
that's,
grains. Like the cotton candy grains on there.
Oh, yes.
that makes so sour.
At some approximation, you've now succeeded at B7. And I wanted to talk a little about B8. What's the central dogma?
I've heard that before, I don't know where it's from.
I remember learning about it.
That sounds really familiar.
Yeah.
What's the central dogma?
What is this?
Sounds like something I felt.
It's like from. Is it the ones that go from vein transcription to.
God.
Genetic information.
Let's all Google that. Central dogma. Central dogma.
What is this? Is that a?
Oh my God, it's DNA makes RNA makes protein.
Oh.
My goodness, I can't wait.
So you're right.
That is the central dogma. So, 8 out of 10 kids know more about the central dogma than the rest of us.
Well, I mean, we learned about it, but I don't remember anything.
How do you not know transcription
Oh,
translation?
no, I know that something.
You know,
I
what's
just
the central
I didn't
dogma?
try central. I've heard the
Transcription
word central.
translation.
Yeah.
It's like this process, right? So it's not.
Yeah, like that's just the name for transcription translation.
Really?
Yeah, I know what it is.
Yes, I know you do. That's what I'm saying. You're more qualified than I am to talk about it. I'm joking. Do you have that one?
Oh, no.
You do, but you need this one.
What? I have that one.
Oh, you have that? I thought.
I studied
Okay.
it.
1, 2. Oh, there's one more. Okay, what can you tell me about a nucleic acid? It's the last macromolecule we need to learn in this class.
It's in DNA.
Huh?
It's in DNA.
It's in DNA
RNA.
and RNA. What are the 3 components of a nucleotide?
Nitrogenous base.
A nitrogenous base, a phosphate, and a ribose, be it deoxyribose or ribose. So one of the pages that I gave you, if I didn't fail, is from the data booklet. In the data booklet, you see ribose and deoxyribose. Are they pentose or hexose sugars? Pentose sugars. If carbon 1 is the carbon on the right, where is the deoxy in deoxyribose? It's 2 deoxyribose. That's how we call it in my subject. 2 deoxyribose. Excellent. So then I want you to scoot around to position 3. What do you think is going to go on what I might call a 3'? Because you know there's multiple things I got to be counting. I got carbons in the nitrogenous base, so I might call those, 1, 2, 3, 4, 5. And so I'm going to call the carbons in my sugar like 1', 2', 3', 4', and 5'. You told me it was a pentose. So it's actually 2' deoxyribose, but if it's just the sugar, it's 2 deoxyribose. So it's a little gross. But what about position 3? What's going to go there? A phosphate group. It's going to make a phosphoester bond. But that phosphate group is also going to bond to the sugar of another nucleotide. And where do you think it would go on the next sugar? The 5'. Oh my God, so when we talk about the 3' and the 5' that we've been talking about since we were in 9th grade, that's why, because we're counting the carbons on the ribose sugar. It goes like a clock. So this is 1, 2, 3, 4, 5. Really am trying to project. Really don't seem to care enough. So one of the things that made me nervous was that while for the sugar, I was pretty sure where everything was going to go, I wasn't totally sure for the nitrogenous base how to group them or where to stick them onto the sugar. Have any thoughts about that?
Wait, how they stick or where they stick?
I'll take either. I'll take anything. So we assume it's going to be a condensation reaction of some type. And so we assume that we're going to use the OH on the ribose. Why? And we're going to find something juicy in that base that it will stick to and, make some magic occur. But when I look at those structures, I'm not sure where they all stick. Do you not feel that feel? What's the other thing that these nitrogenous bases have to do? They have 2 roles. One role being that they have to, make covalent bonds to a nitrogenous base and a phosphate group. Oh, they have to hydrogen bonds. And so there's actually a pairing, right? So DNA is a double helix. And the zipper that holds that double helix together is a whole lot of hydrogen bonds. And the hydrogen bonds are through the paired bases. And so what are the pairs? Everyone agree? Okay. But when I look at those, I notice that some of the structures are bigger than some of the other structures. Do you notice that? So I have the 2 ringers and the 1 ringers. And I would assume for the DNA to be evenly coiled that I need to have a 2-ringer and a 1-ringer lineup. I couldn't have 2 2-ringers or 2 1-ringers because I would have like bulges and it would be kind of disgusting. Okay, so we take the bigger molecules and give it the smaller name. We refer to the 2-ringers as purines and the 1-ringers as pyrimidines. Sarah Munyu, once upon a time, was a teacher here. She has been a teacher here for a long time. I don't think any of you knew her, but she taught me pure as gold. If anyone ever makes me know which one the purines are, they're A and G. I don't know that I ever have to know that, but she taught me that, so I haven't forgotten it. Please don't die. So you told me that there were hydrogen bonds that held these bases together to make the double helix that is DNA. And the hydrogen bonds have to be between A and T, C and G, A and U. Some of you know about Tata boxes and how I'm fascinated with it because it sounds so funny. But why do we have them? What's special about a Tata box?
Wouldn't they have 6? Wait, are you finding?
So a Tata box is an area in DNA where you have only T's and A's. You don't have any G's and C's. And I think it has something.
That's where you start.
That's where you start. Why do you start there? Why do you think it's so nice? Like, I mean, it's not an accident. It's because there's only 2 hydrogen bonds between A and T, and there are 3 hydrogen bonds between G and C. And so I start in a region where it's relatively easy to start opening those 2 strands. Clever, right? Biology's so clever. If it weren't so boring, it'd be so interesting, you know? Like, it's right at that line of fascinating, and oh my gosh, there's so much to memorize. So I wondered if we could figure out where those hydrogen bonds are. And so that's why I gave you the data booklet. Because I've seen the question that's like, show me the hydrogen bonds. And so I wanted to make sure that they were the right orientation, like the one you're gonna have to know, to see if we could figure out how the G and the C make 3, how the T and the A make 2, so that we could draw that picture. Because my understanding of what's one of the many things that's hard in this unit is that like it's very drawing intensive. I know everyone knows what a triglyceride is, but you've got to draw it and you've got to hydrolyze it and you've got to draw the fatty acids and you've got to draw the peptide bonds to make the dipeptide. Like none of the, not all of the words are hard, but like none of the ideas are super hard. They're all condensation reactions, as Breckin pointed out. But like actually writing them down correctly is surprisingly hard, especially if it's not something you've had to do and you've been talking about them with such facility for so long. So I wondered if you could do that. Thank God. Yes, it's a Wednesday today, but I still have many minutes to spend with you, right? Okay. I appreciate your total lack of faith. So I actually thought the activity, I'm not sure if it's the right one. I don't know. Can you do this or not?
What was at the end of the day? I like that. We both want to drink, but
express to you how hard I find this.
Like the single piece of KM.
No, I did. Where's your proof? You have no evidence. Zero. I don't know why you're.
Okay, Brecken has an opinion. That's fantastic.
Like eyebrows or offensive now. Like Pinocchio, because he's got those things where he's like.
Oh, we're now searching it up? That seems kind of like cheating, doesn't it? It's not that I don't know the answer, it's that I wanted us to think about it.
What do we think you think?
So I gave you the structures of the bases, and you guys know that they need to be able to hydrogen bond. And so Brecken has circled the things that he thinks are gonna hydrogen bond, both the donors and the recipients. But I wondered if we could agree on a, as a class. I wondered if the book like wrote them in a useful way, because it surely didn't make it easy for me to make sucrose.
Did you say if it's gonna be, wait, never mind. Would the H on the, for alkene and thymine, for example, would the lone H on the bottom match with the double one O on the left? Cause I didn't know if the H2 would go with the O, cause.
So I don't think it's gonna be this one, because I know that adenine needs to make 2. And this one doesn't have a neighbor. So I think that this is gonna be a recipient, and I think that this is gonna be a donor.
So, oh, so the-
I don't know what anyone else thinks.
Wait,
Do you agree?
why would NH2 donate? Are we bonding to the end of this guy? Like
So
the-
how would NH2 donate a hydrogen? NH2 is a hydrogen bond donor. That means it owns the really positive H. So it's looking for a lone pair on an N, O, or F.
Like, wait, then didn't you say that like where the bond is finished is that N over there?
I haven't said, I asked if you knew,
Oh.
but no one went for it.
What about the O for the thymine?
Okay, so if we go down to the thymine, we need to have something that can take and something that can give.
Oh, then the N is.
And so I believe it's gonna be this NH and this CO.
Can the NH take another?
The NH is gonna be the giver, and the
Oh.
O is gonna be the receiver.
Is it still actually on one of the?
You have them in front of you, like, look at your own thing. I made a photocopy just so you could, like, pout on your own.
Is it so hydrogen bond if there's a C and a CO? And I thought, would it only be the OH on these two?
So, for a hydrogen bond to occur, what we need to have is we need to have a hydrogen directly bonded to an oxygen or a nitrogen. So I am referring to this species as the donor. Somewhere else, I need to have an oxygen that has a lone pair or a nitrogen that has a lone pair. It can have hydrogens or not, I don't really care, it just has to have a lone pair. And it is this interaction that is a hydrogen bond. So when we talk about water, water is both a donor and a receiver. I'm ready for almost nothing, but I'm gonna pretend I'm ready for anything. Well, that's awkward.
Yeah, that's why I was confused.
Because the thymine is actually that.
Thymine, CO, oh yeah, you're right, those don't match. Aren't you the winner? So you're saying this is thymine? Yes?
Yeah, because the data was
And you're saying this is uracil?
that one's thank you.
How are they all wrong?
I was wondering, so like, is one actually green? I was so confused.
Well, the purines are correct.
Was it green?
First, we see if these match. Okay, so cytosine. It has a double bond, it has an NH, it has an O, it has an N, it has an NH2. That looks hot to me. Okay? Thymine. Thymine has an NH, has a CO, has an NH, has a CO. I like it. Okay, I believe that cytosine and thymine are consistent between this and that. Would you like to support that, Margaret? Okay. Please write to Pearson in your free time and let them know that other slide is frightful. So, I'm using a highlighter and I'm gonna highlight my data booklet page to see where the givers and receivers are, to see if I can match it up. You just know how it works?
When you say current recipe, it's just how it works and you can figure it out on the spot.
Can you?
Certified.
I mean, for one,
Thymine, I have the N to the sugars, C double bond O, the NH and the CO. For adenine, that's this NH. Going down to the sugar. I've gotta come over here. And I've gotta have this NH2, and I've gotta have this N. Yeah, like I find this, like I find it hard to believe. Like, do you appreciate what you'd have to draw to make this happen? The night before the test next week? Okay. So, I mean, I hope you appreciate that what we've had to do from the data booklet is take the picture and flip it, right? And Audrey thinks that's easy, but I think it's hard to draw.
In the bonds, like in the first one, the NH2 and the O, what's the finding? There's the NH. Where's the lone N on the adenine? I understand, there's when this one, which lone N is this N?
That's what I'm saying, it's hard, so if I had to draw this, I would have to take this molecule, flip it over,
So then this is next to N.
because it's not this NH, it's this NH. It's the NH in between the two carbonyls. That's why I had to throw away my first piece of paper. You did. Granted, I put a little ball through it, mistake. So I'm clearly trying to express to you one of the questions that I got on a paper 3, and I was like, this is unreasonable. Right? Like this is hard to me. I know there's hydrogen bonds. I don't have difficulty explaining that, but I did have difficulty trying to draw them out. And so I wanted to share that with you, and apparently some of you just see it. And you don't? So now she's gonna try to prove that she can do it? So what is your strategy short of just saying I'm gonna memorize it?
What's it this?
So which is the N that's gonna bond to my my sugar? For any of them, is that in like a kind of conserved place between all of these? Would that help us to figure this out? Can you see if there's a pattern in the end that we're targeting for binding? I appreciate that you can make the face like I'm not speaking the English.
Is it the one with the single bonds?
Is it the one with the single bonds? Yes. So what I was trying to say, and apparently not very effectively, is that I believe in each case it is this NH that is binding to the sugar. So it's sort of the one that's at the bottom or the one that's on the bottom on the right in each case that is what that's gonna attach to the sugar.
So when it's not between the two,
Yes. And so I wondered if by seeing that there is some pattern in how they organized this, that then I could say that maybe it's not awful to say it's on the side opposite that I'm going to have my hydrogen bonding. It's on the side opposite that I'm gonna have my hydrogen bonding. And so I just wondered if there's a strategy we could use so that we didn't have to, like, you have to memorize a little bit, but in the sense of annotating my data booklet, not in the sense of figuring out how to draw this. So I tried to take this and flip it around so that my sugar one was on the left. And now maybe I can imagine that there is a hydrogen bond there and there is a hydrogen bond there. Side is seen, it's gonna be those three. But I found the act of putting the two sugar things on opposite sides so that the bases were facing each other helps me to think about what this might look like.
Wait, so is that whole NH2CN thing hydrogen bonding to this one?
So I think that this H is gonna hydrogen bond to that O. I think this H is gonna hydrogen bond to that N, and I think this H is gonna hydrogen bond to that O.
Oh, so like
So there are 3 hydrogen bonds between G and C, while there are only 2 between T and A or U and A. That's right, but if you've never had to do it before, and you've never thought it, like, I really thought it was not hard until someone asked me to draw it, and then I couldn't do it, and I felt, ill-prepared for something, and I don't want you to experience that. Yes?
But we should have cut these out this time.
So again, this is just something that was hard for me, and it doesn't mean it's hard. It is over. So I think you're gonna strike the data, actually, to a real. I don't know how the methyl plays into that either. But the Walker's next door and he can certainly answer
And
that.
then maybe some of what he did with those were better first.
Margaret, on a scale of 1 to 10, can you do transcription translation? Can you take DNA, turn it into RNA, take RNA and turn it into amino acids?
Currently,
You can say 0.